a little bit about inference in first-order logic. So first we need to create a knowledge base in first-order logic. Okay, there's a previous video on how first-order logic, the syntax of first-order logic. Now we want to create a knowledge base, and we're going to actually ask things to it. So for example, to create a knowledge base, first we have to identify the task. We have to assemble the relevant knowledge. We need to decide on a vocabulary of predicates, functions, and constants, which is what we've done in the previous video. We need to encode general knowledge about the domain, so the rules, which we also described in the previous video. We'll encode a description of the problem, also there, and then we have to post queries to the inference procedure and get answers, right? So basically we give it the intelligence and then we ask questions to it and it'll return the answers. And of course we then debug the knowledge base, and this is pretty iterative process. This video will deal with how we get the machine to do, well, this part, okay? It'll help you debug the knowledge base, but how do we post queries and what is the inference procedure? So, for example, we have this database, right? So if we have a rule that says for all object x such that x is king and x is greedy, then I'm going to conclude that x is evil. You know, if x is John, I can conclude that if John is king and John is greedy, I can conclude that John is king, John is greedy, therefore John is evil. If Richard is king and Richard is greedy, I can conclude that Richard's greedy, then Richard is evil. I can do more complicated inferences. For example, if I know that the father of John is a king, and the father of John is greedy, then I can say that the father of John is evil. That's the idea of inference, is that given some facts that I already know, can I drive these conclusions? And with those conclusions, can I iterate over and answer even more questions? So there's a couple of rules. This syntax is still too complicated. Namely, we have this quantifier here, universal quantifiers and existential quantifiers that will be bugging us for in terms of algorithms. Because we've seen in previous videos about propositional logic that if these were just ands and ors and implications, then, or ands and implications, this would be, we already have algorithms to solve this. What we don't have algorithms to solve for are these for all and quantifiers, universal and existential quantifiers. So we're going to say that the universal instantiation is the for all rule. What we're going to try is, instead of having a for all, right, for all x such that king x and greedy x, let's substitute x by all x's that we know and we create new rules. If it's 17 rules, well then we create 17 rules just like this one, but instead of x we're going to have John, Richard, and so on and so forth. For the existential instantiation, an exists rule, we will just substitute one symbol and use the rule, and then we'll discard the one that had the exists symbol in it. At some point in time, many rules might have the variable x, for example, but the variables here, so this variable x, only works in this rule. If there's another rule with the variable x, it's not the same x, okay? So in order to differentiate, we might create different constants for different rules, and those are called as column constants, okay? Is when we create a new variable just so we don't get confused. And then in computers, for computers to not get confused as well, we will need to create new variable names. All right, so let's suppose we have a knowledge base that says this. For all x such that king is x and greedy and x is greedy, then x is evil. We know that John is king and greedy John, and we know that Richard is the brother of John. Okay. Now we will apply the universal instantiation using all the variables, all possible x's that we know, x John and x Richard. If we use that, because it says for all x, okay, if x is king and x is greedy, then x is evil. So we're going to apply all x's. Let's apply x John. We're going to put king John and greedy John implies evil John. This is basically this rule, but we took away the x and we apply one of the x's. And then we'll do the same with Richard, right? Evil Richard. And then we will add these two rules to the knowledge base and discard this one here. Now we have just propositions. These are symbols. This can be King John can be P, greedy can be Q, right? And we can have P and Q imply whatever, Z, right? So this is just propositions. We will tell to propositions. Now, the other thing that's interesting is whether some of these are true, some of these are not true, right? Now, suppose instead that our knowledge base has the same rule for all x, such that x is king and greedy, and x is greedy, then x is evil. And we only have the John is king, but we also know that for all y, this would be as calling constants. It could be for all x, greedy x, but in order not to get confused with this x, I'm just going to say y. So for all y, y is greedy. What I'm saying is that everybody is greedy. And I know that John is king. Obviously, for a human, if John is king, that's x is John, right? And John is greedy, and we know that John is greedy because everybody is greedy, right? Then that we could conclude that John is evil in this case. But we don't have the same variables. So what do? We do universal instantiation, which is this for all sign, using all possible substitutions. So one substitution is this one that works. This substitution satisfies this and this. Is x is John and y is John, right? So because John is the only symbol we have here. If we had more symbols here, well, x is definitely John here. King of x, king x, x is going to be John. Now we also have that y, right? Y is John. So then we eliminate this guy, and we will have a rule that says greedy John. And then we can substitute this rule over there, right? So with this, if I grab all the variables in my knowledge base and I substitute the x with John and the y's with John, I will get rid of both universal instantiations, and I will have a knowledge base full of propositions. Now there's a more general rule to do this, and it says the following. Basically, it says that if I have a premise here on this side that implies a conclusion, if there's a substitution such as x John, y John, if there's a substitution such that all the premises here are satisfied in the knowledge base, okay? If there's substitution satisfies these premises in the knowledge base and the premises here, then I can just add the conclusion to the knowledge base. And we do it more formally like this. If there's prepositions and then another set of analogous prepositions and a conclusion Q, and there's a substitution theta such that if we substitute the analogous rules, right? If that substitution also works for other rules such that these rules together drive to a conclusion. If we can find a substitution that works for these, remember these are the same predicates as these ones here, okay? They just have different values in them. One has John, the other one has X, right? If we can find a substitution that works for all the predicates in my knowledge base that are involved in an implication to a conclusion, then I can substitute that theta, all the substitutions that worked, in the conclusion. For example, if I know that in this previous example here, well, it's too noisy here, but if we have king x and greedy x imply evil x, okay? King x and greedy x imply evil x, and we also have king John, greedy y, and a substitution x John, y John, this substitution, theta, satisfies both these premises at the same time, okay? Therefore, I can substitute theta in this conclusion. And what is x in my substitution? X is John, so I can say that John is evil. See how algorithmic this is. If I can find substitutions here, and I know that these predicates are the same ones involved in a conclusion, then I can just substitute these variables into whatever variables are in this term Q and just conclude that and add it to the knowledge base. We're going to see an example of that. The way we do this is via unification. Okay, there's an algorithm for unification. I'm not going to show it here, but you can find Wikipedia or Google algorithm for unification, and you will find it. We'll unify two clauses, two propositional clauses, and the unification will return a substitution, where we can substitute, where the substitution for P is going to be the same substitution for Q. For example, if we I'm going to look at this. Unify, for example, this preposition, knows John X with knows John Jane. Well, the substitution here, basically these two will be the same if X is Jane. So my substitution for these two things to be the same is X is Jane. Now, for example, knows John X and knows Y Bill, a substitution that would make these two things equal is that X is Bill and Y is John, right? So then both will say knows John Bill, right? If I want to unify knows John X and knows Y mother Y, for example, knows Y mother Y, I will substitute Y with John and X with mother of John, right? Because mother Y and Y is John. So then I can ask variable. This will help me to look at my rules and ask, for example, who knows John? Or whom does John knows X? So whom does John know, right? X. And then if I unify all of the knows John rules in my knowledge base, I will end up with a substitution that will be the answer to who knows John. Let's look at one seminal problem for this. The law says that this will be the whole thing, everything put together, syntax and unification put together. The law says that it is a crime for an American to sell weapons to hostile nations. The country No-No, an enemy of America, has some missiles, and all of its missiles were sold to it by Colonel West, who is an American. Can we prove that Colonel West is a criminal? Not West, but West is a criminal. Well, let's look at the rules. The law says that it's a crime for an American to sell weapons to hostile nations, and so on and so forth. So, first, the law says that it's a crime for an American to sell weapons to hostile nations. So if X is an American and Y is a weapon and X sells the weapon Y to Z and Z is a hostile nation, then this X who sold it in the first place is a criminal. That's how we will write this rule. Now we also know the country of No-No, an enemy of America. So we know that No-No is an enemy of America, right? Has some missiles. We know that No-No owns missiles, okay? No-No has some missiles. Now, I don't put some missiles, but I will, because I know that No-No has some missiles, so I'm going to say that there's one variable, one object called M1, which is a missile. So No-No owning some missiles, that's an existential quantifier. I will just replace one instance. M1 is going to be a missile, and No-No owns a missile. And all of its missiles were sold to it by Colonel West. So, I also know that if X is a missile, X is a weapon, and here's why this is important, because I know that No-No owns a missile, but I also know as a human that missiles are weapons, right? So when I say weapon Y, if I can find a substitution via the missile, right? I know the missiles are weapons. I need to arrive at this rule at some point to determine whether West is a criminal. And this rule here talks about weapons, not missiles. So I need something that links a missile with a weapon. Now also, I know that that all the missiles were sold to it by Colonel West. So if X is a missile and No-No owns that missile, then that implies that West sold that missile to No-No. Then also we know that here the rules talks in terms of hostility. Well, we know that any enemy of America is hostile from the American point of view. And then we also know that West is an American. So we've translated this whole problem into rules in a knowledge base. Okay? Now this is my knowledge base. Now let's start doing inference on it. One can represent this as an and/or tree. We've seen this before, but so you can use search algorithms to resolve this. But let's do this. Here, we know that missile M1, this is one substitution, so we do unification here, right? And here. So then we'll end up with weapon M1, and the other thing that we know, we'll end up with weapon M1, and also we know that Nana owns a missile, right? Nana owns M1, so we'll also unify this. There's a substitution that gets own and missile, substitute both of these such that these two rules are satisfied. Therefore, I will put this substitution, I will use the substitution here in this conclusion. That's the generalized modus ponens that we talked about. So R5, rule 5 is satisfied with X M1. So in rule 9, cells West M1 no is added. This is what happens. Also, rule 4 is satisfied with X M1, and the rule weapon in M1 is added. So this rule here, rule 4, is satisfied with M1. So then I add weapon in M1 to the knowledge base. And then rule 6 is satisfied with no, and hostile no is added. So rule here, enemy X America is satisfied with this one. We can unify those two, and then we can add hostile no to the knowledge base. Now our knowledge base has 9, 10, 11 rules. These are the rules I'm adding. Okay? And then if you add these rules, you iterate again in the knowledge base until you can make no inferences, right? But you can iterate again until you find the conclusion, or it can make no inferences. So we iterate again, and rule 1 now is satisfied with this substitution. X West, Y is M1, and Z is no. Because we establish these cells. We establish the weapon M1, and we establish hostile no. And if we look at rule 1, American X is satisfied with West. So X is West. There's no other alternative. Weapon Y, well, our knowledge base will have this weapon M1. So M1 satisfied the variable Y, right? And then cells X, Y, Z. So cells West, M1. What else is there? What can we unify it with? Oh, we have a rule 9 here that says cells West M1 no. So we use no as Z. So then, so we can satisfy this one, and we also satisfied hostile. I recommend you do these steps and replace this with the 2 iterations. So therefore, after we've done all this, we can unify all of the terms of rule 1, which is the one that has the conclusion of someone being a criminal, which is the question, who is a criminal, right? So we will substitute everything we can via unification, and as soon as we can substitute all the terms in the premise that leads to the conclusion we're looking for, okay, at least the relationship we're looking for, then we can answer that. We can use that substitution here. And the substitution was X, Y, Z, and criminal X. So of this substitution that satisfies this part here, we will just use X because that's what this one uses. If it uses more, we'll use more. But then we've established that West is a criminal. So is West a criminal? Well, if we do the inferences, at some point the knowledge base is going to say criminal West. And when we ask whether West is a criminal, we're going to get true for the value of that. So once we have the facts, all the facts that we can possibly infer, they will evaluate to true or false. We can apply forward chaining, backward chaining, and resolution, which are algorithms that we already seen in previous videos. And the key is to understand how unification works. Okay, this is the same as logical agents. The key is to understand unification, and the power here comes that we can this language is much more expressive than simply propositional logic. We can give it more rules with unification.